Hi, welcome back. So this is lecture 46 in this course on Bayesian data analysis for behavioral sciences. The topic of this lecture is posterior predictive checks. So from this lecture onwards, we are starting um, model comparison. So how do we compare model, or how do we evaluate a model in the Bayesian framework? And this is the first lecture in this model comparison module. Okay, why do we need these lectures on model comparison? I think that motivation is quite clear even from the very first class I took in this course, that the process of statistical inference is incomplete unless we compare our competing assumptions, right? So for example, let's say I have collected some data in my experiment and I assumed that my data comes from an underlying generative process f of theta. Okay, so that's my assumption. It can come from a theoretical position as well. So let's say a theory says that the data in this experiment comes from an underlying generative process f of theta. Okay. Then we go on and estimate that parameter theta, and we try to get an idea that under what value of theta you might generate this data given this particular assumption. Okay. But inference is incomplete at this point, because the goal of the inference is to know what is this true generative process. When we just do parameter estimation, it does not give us really much about what is the true generative process. It only tells you that under the assumption that f of theta is the true generative process, then these values of theta are likely to generate the data. Okay, so inference is not complete here. For inference, what we really need is that we will compare this particular assumption f of theta against some competing assumption, against some other candidate assumption, let's say g of phi. Okay, if f of theta is better at explaining the data compared to g of phi, okay, then we can make a claim that f of theta is probably closer to the truth compared to g of phi. Okay, and that's the only kind of inference you can make. Okay, remember, so there are no absolute inference you can make. You cannot say that this is a good model of the underlying generative process. You can only say whether this model is a better model of the underlying generative process compared to some other model. Okay, so we can only make these relative statements, and that's how we see evidence in a statistical inference, right? So for example, when you ask this question, that whether there is an evidence, whether there is some evidence for this theory A, okay, then what we do is that we compare theory A against some baseline theory, or let's say some theory B, given some data. And what we actually compare is that whether theory A or theory B, which one of these is better at explaining the data. If theory A is better, then we can say that theory A is basically a better theory for this particular process because it explains the data better. And so the evidence that way is relative, right? So we cannot talk about evidence without comparing our theory or our model against some competing model or a theory, right? So these lectures on model comparison are going to be very, very crucial for hypothesis testing, theory testing, or to quantify evidence for any model of your interest, right? So from this point on, we are moving in the direction of basically figuring out that how do we quantify evidence for a model compared to some other candidate model. Okay, so basically the methods that we are going to take a look at, all these methods are about evidence quantification. So they quantify how much evidence is there for one model compared to other. But we will need to take some perspective, what we will call evidence, and exactly in what situation you can say that some particular model is closer to the truth compared to some other model, right? Ultimately, our goal is to figure out a model which is closer to the truth compared to others, right? That's how we reach nearer and nearer to the truth. Okay, we explore a lot of candidate models, right? Eventually, in sciences, that's how it progresses, right? We explore candidate models, and we want to reach closer and closer to the true generative process. Okay, so we explore more and more models which are able to explain the data better. Okay, so that's why model comparison and model selection are really important, right? So this is the goal of these next few lectures. We will learn a couple of methods which you can use for model comparison in the Bayesian framework. Okay. So let us start with this question. Okay. When do you say that a particular model is better model or is a good model? Okay. Let's say you did an experiment and you collected some data, right? How can you say that some model 1 or whatever model X is a good model or not? Okay, so let us talk about this. So one perspective to look at this is, well, that my model is a better model or a good model if it can predict that what kind of outcomes I will get in some future experiment, or let's say an unseen experiment. So even before, let's say, collecting any data, you have a model and that model makes some prediction. Okay. If that model makes right predictions, that means if the model predictions are supported by actually observed data, then that means that's a, let's say, a better model or a good model. So that's a property you want in a good model of underlying generative process, that it should make accurate predictions. So that's the first thing we need, predictive accuracy. Second, if let's say you have two equally accurate model in terms of making predictions, then you would prefer a model which is simpler, a model that provides that model that has fewer parameters and provides simpler explanation for the same phenomena, right? So these two sort of criteria are often taken into account when we select a model for the underlying generative process. Okay? One, that it should have a better predictive accuracy. Second, it should be simpler, it should have fewer assumptions. So let me write these two perspectives and then we can move on what is the point of posterior predictive checks in this context. Okay. So the first criteria we can take into account is predictive accuracy of a model, that how good is the model at predicting future data, that we call predictive accuracy of a model. Second, we want to take into account simplicity of the model. So we prefer simpler model over complex model. Simplicity for now we can define in terms of, let's say, how many parameters are there in the model. Okay. So predictive accuracy of a model and simplicity of the model. Okay. What approach do we use to evaluate the fit of a model? That model is able to predict, or let's say to evaluate predictive accuracy of a model. So how do we compute predictive accuracy of a model? Okay. What approach can we take in this direction? So one approach that we slightly explored in one of the previous lectures was that you can actually generate posterior predictions from the model and then compare these posterior predictions against against the data, same data that you use to train the model, to verify whether the model is able to predict whether these posterior predictions match, align with the actual data, right? That was basically, we generated posterior predictive data from the model and compared posterior predictive data against observed data. Okay, that was one approach. Okay, you will see that in many articles or any methods you will find online or in books, this is actually one of the frequently used method to assess the model fit. So people often assess model fit using this approach. What they do, that based on parameter estimates you have, so let's say your model was something like this, you are interested in explaining this outcome y. Let's say you assume that yi comes from this model f of y theta, okay, and you observe some data, let's say y obs. You fit the model to this data. Basically, that means we estimate our parameter theta, and let's say theta comes out to be theta hat. In frequentist framework, it would be just a point value. Let's say you obtain a point value of this parameter theta. Now, what people do is that they generate predictions, okay, from this model conditional on this particular value of theta, that is theta hat. So, this is estimated value of theta. So, this model is generating future predictions conditional on this estimate of this parameter theta, and this estimate is actually conditional on something. Okay. This estimate we have obtained, it is based on this training data. This was the data that you used to estimate this parameter, right. So, this is this data y obs, right. So, this is conditional on y obs actually. Okay. So, now we generate basically some data based on this estimate of the parameter theta hat. Okay. Now, you compare y pred and y obs. Okay. If they totally align with each other, then people claim that, well, this is a good fit. If this does not align, then they will say that this is a bad fit. Okay. So, this is one of the approach. Okay. In Bayesian framework, this approach will become posterior predictive check. Okay. How? So, let us think about a Bayesian model, and let us see how the same approach would work in the Bayesian framework. So, let us say this is your model. You are interested in, hypothetically, let us say in modeling an outcome y, yi. Okay. It could be, let us say, reaction time or responses or whatever, response accuracy. So, let us say yi comes from this distribution. So, this is our likelihood function f y theta. Okay. This is our likelihood function, and the parameter theta has some prior distribution, let us say p of theta. So, let us say this is your model. Okay. Let us call it model M1. Now, what you do next? We estimate the posterior distribution of theta. So, how do we estimate posterior distribution of theta? We estimate p theta given y using, let us say, Markov chain Monte Carlo or Hamiltonian Monte Carlo, using some algorithm or using some existing package, let us say BRMS. We estimate posterior distribution of theta by applying Bayes theorem here. Okay. So, let us say the data that we have, that we are using to estimate posterior, is y obs. So, this is something we observe in a particular experiment. Okay. So, let me write it that way. So, theta y obs here as well. Likelihood will also depend on data, prior density of theta divided by marginal likelihood. Okay. This is how we obtain the posterior distribution of theta. Okay. All right. So, let us say by applying some algorithm, let us say Hamiltonian Monte Carlo or MCMC, we obtain the posterior distribution of theta. Now, this is an estimated distribution, and it is basically not the true distribution, it is estimated and approximated using an algorithm. So, it is better to write it this way. Okay. So, this is an estimate of this parameter theta. This is not the true value of the parameter theta. This is estimated based on this data y obs, right. So, I always write estimated distribution or estimated values using this hat symbol. Okay. So, I will call it estimated posterior distribution of theta. So, after observing this data y obs, this is what I have estimated, right. Now, how do I generate posterior predictions? Do you remember? Well, in order to generate posterior predictions, what I will do, I will sample a lot of values of theta from its posterior distribution. So, let us say theta z from its posterior distribution. Okay. Basically, you are drawing samples from the posterior, or let us say whatever samples you have collected from the posterior, you use those samples, right. So, use samples from the posterior, and conditional on each sample from the posterior, you generate new data. So, I will call it y-pred. So, y-pred will come from our likelihood assumption basically, which was f y theta, f y and theta j, because theta j is a sample from the posterior. So, this is what we use to generate future data. Okay. Basically, what model predicts after estimating its posterior distribution of the parameter. So, now we are generating future predictions based on samples from the posterior. So, this is called posterior predictive data. Okay. You can call it posterior predictive data. Okay. Fine. Now what you can do is this, that you compare this posterior predictive data against the actual observed data that you used to estimate the posterior distribution. So, y-obs was the data that we used to estimate the posterior. Now, you compare these predicted data points against these observed data points. Okay. If they are close to each other, okay, if y-pred and y-obs are close to each other, then you say that the model fit is good, otherwise model fit is bad. Okay. So, this is the approach that is used in some methods of model evaluation. For example, AIC, BIC, likelihood ratio test, right? Not exactly this, but it uses the same idea. I will explain how those approaches work. But this is posterior predictive check, so that you compare your posterior predictive data against the actual observed data that you use to train the model. Okay, and this will give you some measure of how good is the model fit. But there is a serious problem here, and the problem is so serious that we cannot use this method to actually compare our candidate models. We cannot use this model to quantify evidence. Okay. So, basically this method is kind of useless if we want to quantify evidence, if you want to quantify predictive accuracy of a model. Okay. So, there is a serious problem here. Can you figure out what is the problem in this approach? Well, the problem is this, that you used the same data to train your model, which is basically to estimate for parameter estimation. You use the same model to train the model, basically to obtain posterior distribution of theta, and you use the same data to test your model, because then you compare y-pred against y-obs. You are using same data twice. You are using same data to train the model and then to test the predictive accuracy of the model. This is called overfitting. So, you are using same data points to train your model and then to test the predictive accuracy of the model. So, this is a problem. Why this is a problem? Because often whatever sample of data you have, let us say y-obs, it would contain certain regular features of the data and certain irregular features of the data. So, let us say some regular features and some irregular features. Okay. When you fit the model to this data, the model learns both of these, regular as well as irregular. It does not know basically what are the outliers or irregular features and what are the regular features that are generated by true generative process, because data are often noisy, right. So, the model will learn every kind of information from this data. Okay. So, when you compare these predictions against the same data, they are always going to look good. Okay. But when you compare these same predictions against, let us say, some future data, okay. So, some data that you collect in some future experiment, then your posterior predictions might miserably fail. Okay. So, the same model that works for y-obs might miserably fail when it comes to explaining some future data. Okay. This is because model often learns irregular features from the data, and it would basically the predictions the model is generating are biased to predict the same data, right? It would predict the same data, because if your model is complex enough, it would learn most of the information that is there in the data, and then when you generate predictions, it would be able to predict the same data. There is no problem in doing that, but the problem is that it won't be able to predict future data, okay, or may not be able to predict future data. So even if the model is really good at predicting the same data, y obs, it might be really bad at predicting future data, and we do not want that, okay, because what predictive accuracy of a model means is that the model should be able to predict any data set that comes from the same generative process, or any future data that comes from the same generative process. Why? Because the way we think about predictive accuracy. So, what do we think about predictive accuracy? So, what is predictive accuracy for us? Okay. What is predictive accuracy? Well, how good is the model at predicting data or at predicting outcomes in an experiment? Fine, but outcomes from which experiment? You can basically, let's say, repeat the same experiment multiple times at multiple places, right? And supposedly the whatever outcomes you observe in that experiment are coming from the same true generative process. Okay, so you can draw samples from the same generative process multiple times. Okay, all those are observations. Okay? So with what observations we are considering when we measure predictive accuracy of the model? Well, the idea is this, that let's say this is our true generative process. Okay, and we do repeated experiments. Let's say we do multiple experiments where outcomes are supposedly coming from the same true generative process. So let's say in experiment 1, the outcome we get is y obs 1. In experiment 2, we get y obs 2. Here we get y obs 3. Here we get y obs 4. Here we get y obs 5. So let's say these are 5 experiments we did. Okay, let's say at multiple places or whatever. These 5 experiments we did. It's the same experiment. Let's say repeated the same experiment 5 times. Okay, so you can reasonably assume that the outcomes in these experiments are coming from the same true generative process. Okay, so what would be a good model? A good model will be the one which can correctly predict these all 5. Okay, a good model will be the one which can predict these all 5. Why? Because what we want, the goal of the inference, is to reach closer to this true generative process. Okay, if the assumptions you have made or the model that you have specified, let's say M1, if your model M1 is close to the true generative process, then it should be able to predict all these outcomes in all these experiments, right? If your model is bad, let's say really far from true generative process, then it would generate very different kind of predictions. Basically, it won't be able to predict these data points, right? It won't be able to accurately predict the observed data, right? If it is close to the true generative process, it should be able to predict all seen, unseen data coming from that particular generative process, right? So essentially, it is not sufficient that your model is able to predict the same data that you use to train the model. Okay, that wouldn't make sense, because that can happen due to overfitting. But if the model is unable to predict unseen data, then that's not a good model. Okay, the model should be able to predict future data, unseen data, and that's very important for us. Okay, so that's the measure of predictive accuracy we are going to explore. Okay, so we are going to redefine predictive accuracy in terms of how good is the model at predicting future data. Okay, or let's say more precisely, how accurately the model can predict future or unseen data. Okay. So, our goal is to come up with measures or matrices that can give us how accurately the model can predict future data. Okay. So, we need to measure this thing. Okay. So, given any model and given some data, we want to quantify that how accurately model can predict future or unseen data. Okay. And there would be challenge here, because most of the times we do not have unseen or future data, we have only access to one data set, right. Then how do we quantify the model? Well, in that case you need to split your data into some training portion and some unseen portion, let us say test set, training set and test set. So, you train the model on one portion of the data and test its predictive accuracy on the remaining portion of the data, right. That is called cross validation. We will explore that as one of the methods. Okay. But for now, first of all, our goal is to think about what measure should I use to capture predictive accuracy of a model. Okay. So, given some unseen data, how do I measure predictive accuracy of a model? So, I need some mathematical measurement of that. Okay. So, that would be the goal of the next lecture. Now, coming back to posterior predictive checks, well, so this is the idea that you compare these posterior predictions of the model against the observed data. Okay. And as we discussed, that this comparison is not sufficient to quantify evidence for a model or to quantify predictive accuracy of a model. Okay. So, this is not a measure of predictive accuracy of a model. Okay. Predictive accuracy should be the that how accurately model can predict future or unseen data, but in this case this was not unseen data. Okay. This is the same data that you use to train the model. Okay. This is also called basically in sample model evaluation. You are using the same sample to train the model and to test the model. Okay. But that does not mean that posterior predictive checks are useless. Okay. They are useful, but not for quantifying a model performance or model's predictive accuracy or for quantifying evidence. They are useful for something else. Okay. In what sense they are useful? Well, one important use case of posterior predictive checks is that whether likelihood assumption is reasonable. So, using posterior predictive checks, we can assess whether our likelihood assumption is reasonable or not. Okay. So, for example, let us say in an experiment you collect some reaction time data, okay, some response time data, and the actual distribution of response times is typically something like this. Okay. So, this is the response times you collected in an experiment. Now, what likelihood assumption would you make about response time? So, let us say response time in ith trial comes from. So, one typical assumption people have made in the field is that RTIs come from a normal distribution with parameter mu and sigma. Okay. Right. Now, this is the likelihood assumption. Now, using PPC, you can actually check whether your likelihood assumption, which is normal, you assumed a normal likelihood here, whether this is a reasonable assumption given these data points or not. Okay. So, PPC is very useful for that. Okay. So, basically you will follow the same approach, you will generate posterior predictions, you will compare posterior predictions against observed data, and if posterior predictions look off, if they look different from the observed data, that means your likelihood assumption is unreasonable. Okay. And there is intuition behind this. So, because this is the actual distribution of the data, if you assume that these reaction times are normally distributed, you will estimate some value of mu and sigma. So, let us say you estimated mu to be 300 and sigma to be 50. Okay. And when you generate posterior predictions from this distribution, so these are estimated values of mu and sigma, and when you generate posterior predictions based on these values of mu and sigma, the posterior predictions would look something like this. Basically, your posterior predictions will remain normally distributed. They won't be able to predict these long tails, okay, because that's a constraint of your model. You assumed a normal likelihood, so it can't predict log normally distributed reading times or reaction times, right? So that's why certain properties of the observed data won't be captured by your likelihood assumption. Okay, so you can use posterior predictive checks to assess how good is your likelihood assumption, whether your likelihood assumption is really bad, like it's unreasonable or not. So for example, you can compare posterior predictive checks for this likelihood versus this likelihood. For log normal likelihood, you will get much better results, right, with posterior predictive checks. Okay, how to do it in principle? Basically, what you can do, so let's say this is your observed data, RT obs. I'm just telling it for this example. So let's say this is your actual data, RT obs. Okay. Now your likelihood assumption here, when you assume a normal likelihood, is RTI comes from normal mu sigma. Here you assume RTI comes from log normal mu sigma, and then you have prior on mu, and here you have prior on mu. These are different mu parameters. You have prior on sigma, you have prior on sigma. Okay, so these are your models, competing models. Now you fit the model to this data RT obs in both these cases. So when you fit the model, you will estimate mu given this data, and you would estimate sigma given this data. Here as well, you will estimate mu given this data, and you will estimate sigma given this data, basically posterior distribution of mu and sigma. Now given these posterior distributions, you will basically draw samples of mu j and sigma j from their posterior distributions, okay, in both the cases. Okay. And based on these samples from the posterior, you would generate some future predictions. It's conditional on each sample from the posterior. So let's call it ypred j. Ypred j is jth sample. These are jth samples from your posterior distribution, and corresponding to each sample from the posterior, you would generate a sample, a posterior predictive sample, right? From what? In this case, it comes from normal distribution. So conditional on mu j and sigma j. In this case, ypred j, it comes from log normal mu j and sigma j. Okay. So this is jth sample. Okay. So you will obtain ypred 1, ypred 2, right, ypred 3, ypred n. So if you draw n samples from the posterior distribution, you will get n posterior predictive samples. Okay, each of them would contain, let's say, whatever number of observations you have in your experiment. Let's say n observations, okay, or n data points. Now you want to compare whether certain properties of the observed data are not captured by your predicted data. Okay, so in order to do that, what you can do, you can calculate certain test statistics or summary statistics of your predicted data. So let's say in predicted data, you calculated mean of all these samples. So you have multiple samples of ypred j, ypred 1, ypred 2, you calculated mean of all these samples and compared the distribution of these means against the mean of the observed data. I can draw actually a plot. So let's say this represents the mean of predicted samples, posterior predictive data, right? And this line represents mean of the observed data. Okay, and this is the distribution of means of predicted data. Okay, so if you get a graph like this, that means the model is able to capture the mean summary statistic of the observed data. Okay, so that means the likelihood assumption is not too bad. Okay, but if you get a plot like this, okay, let's say this is the distribution of mean of predicted data and this is the mean of the observed data. Okay, that means your model predictions are not able to capture this summary statistic of the observed data. Okay, so that means your likelihood assumption might be bad. Okay, so you need to recheck your likelihood assumption. So you can apply this to log normal versus normal likelihood and try, for example, this summary statistic that 97.5% quartile of the predicted sample versus 97.5% quartile of the observed sample. So basically the larger values in the sample. So we are comparing larger values in the sample. So if you assumed a normal likelihood, larger values in the sample will be relatively small. In this observed data, they would be large because observed data has longer tails, right? So the normal likelihood won't be able to capture that. Okay. So then you would know that, but this won't be the case with log normal likelihood. So you can use this for model comparison. You can see this in detail how to implement it in R in my lecture notes, but I'm not going to go into details, more details of this, because this is not very important for the purpose of evaluating predictive accuracy of a model. So this is not the main point of these lectures. Okay? But I just gave you a brief overview of posterior predictive checks, and I also discussed that why this cannot be used as a measure of predictive accuracy of the model, but this has utility in assessing whether your likelihood assumption is reasonable or not. Now, to measure the predictive accuracy of a model, we will need different kind of measurements. We need different kind of mathematical measures. Okay, that we will see in the next lecture. All right, so I will stop here and see you in the next lecture. Thank you.